really fundamental but also pretty weird about the quantum world. Particle spin.
That's right. And forget thinking about tiny balls actually, spinning around. It's not like that.
No, it's this intrinsic quantum thing. And we're going to get into a particularly fascinating corner of it, particles, with spin five-halves. Sounds complex.
It is a bit, but we'll build up to it. We'll start with, what spin is, fundamentally, how it helps us sort particles.
Okay.
And then, we'll venture into the higher spins like three-halves and eventually five-halves.
All right, so let's start there. Spin, not a spinning top. What is it then?
It's an inherent angular momentum, like mass or charge. It's just a property a particle has. And it's quantized.
Quantized meaning it only comes in specific amounts.
Exactly. We use a quantum number, is, to describe it. And is can be an integer, 0, 1, 2.
Like photons.
Like photons, yeah. Or Higgs boson. Those are bosons.
Or it can be a half integer, like 1/2, 3/2.
Right. And those are the fermions, like electrons, quarks, the stuff matter is made of.
So these two families, bosons and fermions, they behave differently because of their spin.
Fundamentally different. It comes down to statistics. Bosons follow Bose-Einstein statistics. Think of them as sociable. Multiple identical bosons can pile into the same quantum state. No problem.
Okay.
Fermions, though, they follow Fermi-Dirac statistics. And they obey the Pauli Exclusion Principle.
Ah, Pauli. No two identical fermions in the same state at the same time.
Exactly. And that's huge. It's why atoms have structure, why electron shells fill up the way they do, why matter is stable, really. It underpins chemistry.
Wow. Okay. So spin isn't just a number, it has a direction, too. Sort of.
Sort of, yeah. We talk about its projection along an axis, usually the z-axis. That projection is also quantized.
Meaning it can only point in certain allowed directions relative to that axis.
Precisely. For spin's particle, you get 2's plus 1 possible values for that projection. They range from s to plus s in steps of 1.
So for spin 1/2, like an electron, 2 times a half is 1, plus 1 is 2. 2 states.
Yep. Minus 1/2 and plus 1/2. We call it spin down and spin up, like a little arrow that can only point along our chosen axis, either kind of down or kind of up.
Okay, I think I've got the basics. So our mission for this deep dive is to take this understanding and apply it first to the familiar spin 1/2 guys.
But workhorses.
Then move to the slightly more exotic spin 3/2.
Getting warmer.
And finally tackle these elusive theoretical spin 5/2 particles based on the analysis we've reviewed.
Let's do it, starting with spin 1/2.
Right. These are everywhere. The building blocks of matter, really common. We understand them pretty well.
Extremely well. You've got electrons, positrons, all 6 quarks, up, down, charm, strange, top, bottom, neutrinos too.
And even things like protons and neutrons, which are made of quarks, end up with a total spin of 1/2, right?
That's right. The combination gives them that overall spin 1/2 property.
And just 2 spin states,
Yeah.
up and down. Why are they so incredibly important besides just being building blocks?
Well, being the building blocks is obviously key. Quarks and leptons form all matter. But then, like we said, the Pauli principle is vital for atomic structure, the periodic table, all of chemistry.
It's hard to overstate that.
Totally. And then there's the Dirac equation. Paul Dirac developed it to describe electrons relativistically, and boom, it predicted antimatter. Just fell out of the math.
Which was later discovered. Amazing.
Truly remarkable. Plus, their spin gives charged spin 1/2 particles an intrinsic magnetic moment, like tiny magnets.
And that's the basis for things like MRI.
Exactly. Nuclear magnetic resonance, NMR, which is MRI, and electron paramagnetic resonance, EPR. Powerful tools in medicine, chemistry, materials science, all thanks to spin 1/2.
Okay, so spin 1/2 is fundamental, well understood, crucial. Now, spin 3/2. Things get weirder.
Yeah, a bit. You don't find fundamental spin 3/2 particles just lying around in the standard model like electrons.
So where do they show up?
Mostly as excited states of other particles, composite particles, or in theories that go beyond the standard model.
Okay, examples.
The classic ones are the delta baryons. Think of them as pumped-up, high-energy versions of protons and neutrons.
Made of the same quarks, but spun up differently.
Kinda, yeah. The quark spins are aligned to give a total of 3/2. They're unstable, resonances we call them, delta plus plus, delta 0, delta minus.
And there was another one, omega.
Ah, yes, the omega minus, made of 3 strange quarks. Its discovery was a huge win for the quark model back in the 60s. Also, spin 3/2.
So those are composite. What about fundamental ones, theoretical ones?
That's where you get things like, well, the gravitino. if the supersymmetry, or CSY, is correct.
That theory that partners every known particle with a superpartner.
Right. CSY predicts the graviton, the gravity force carrier, has a superpartner called the gravitino, and it would have spin 3/2.
But we haven't found the gravitino or any superpartners yet.
No. Still hypothetical.
Yeah.
Very important theoretically, but unobserved.
Okay. And a spin 3/2 particle, how many spin states does it have? 2's plus 1.
2 times 3/2 is 3 plus 1. 4 states.
4 states. Minus 3/2, minus 1/2, plus 1/2, plus 3/2.
You got it.
So what's the big deal about these then? Why study the deltas or hope to find a gravitino?
Studying the deltas and omegas, hadron spectroscopy, tells us a ton about the strong force, the force holding quarks together inside protons and neutrons. It reveals hadron structure.
Okay, understanding the building blocks better.
Exactly. And the gravitino. While finding it would be massive evidence for CSY and could be a key link between gravity and the other forces, a piece of the theory of everything puzzle.
It's not easy, theoretically speaking. The analysis mentioned problem.
Oh, yeah. Big problems.
Yeah.
Describing interacting particles with spin higher than 1 gets nasty. There's the Rarita-Schwinger equation for free spin 3/2 particles.
But when you add interactions, forces,
It gets dicey. You can run into issues like acausality effects happening before causes, faster than light stuff potentially, or loss of unitarity, meaning probabilities don't add up to 100%, which breaks quantum mechanics.
that sounds bad.
It is. It's called the Veloz-Wanziger problem.
Yeah.
You often need fancier frameworks like ITHUSY or string theory to even try and make sense of interacting spin 3/2 particles consistently. It's tricky.
Right, so the complexity definitely ramps up, which brings us to spin 5/2. Strap in.
Definitely. Spin 5/2. Well, fundamental particles with that spin are just not in the standard model, period.
So if they exist at all, they'd have to be.
Either extremely high energy excited states of composites like baryons.
It's like super excited deltas or something?
Sort of, yeah. 3 quarks whizzing around with a huge amount of total angular momentum adding up to 5/2. They'd be incredibly massive, decay almost instantly. You'd hunt for them as resonances in collider data.
Looking for bumps in the graphs?
Exactly. By reconstructing decay products. Or they could pop up in some really out there theories, beyond the standard model stuff.
Of what kind of theories?
Maybe theories with extra dimensions, like Kaluza-Klein theories, or certain corners of string theory, perhaps. But honestly, this is highly speculative territory.
So, bottom line, no confirmed fundamental spin 5/2 particle has ever been seen.
Nope. None. 0 confirmed sightings.
Okay, and the number of spin states? 2's plus 1 again.
2 times 5/2 is 5 plus 1.
6 states. Minus 5/2, minus 3/2, minus 1/2, plus 1/2, plus 3/2, plus 5/2. Wow.
Yeah, more internal complexity, more ways its spin can orient itself.
So if finding one would be so huge, what makes them even harder to deal with theoretically than spin 3/2?
Oh, the problems get magnified significantly. For starters, describing these higher spin fields needs even more mathematical components, but these often bring in redundant, unphysical information that you have to carefully constrain. It's mathematically very awkward.
More pieces that don't quite fit.
Right. And then trying to make them interact consistently with other particles while respecting fundamental principles, causality, unitarity, Lorentz invariance. It's incredibly difficult. The usual methods like gauge principles that work beautifully for spin 1 force carriers like photons just don't translate easily.
It sounds like the math just fights back harder.
It really does. And then there's renormalizability.
The issue where calculations blow up to infinity.
Pretty much. Theories with interacting high-spin particles are often non-renormalizable. You get infinities you can't systematically cancel out, especially at high energies where these particles would matter most. It means the theory kind of breaks down and can't make reliable predictions in that regime.
So a major roadblock for predictive power.
A huge one. It severely limits what you can calculate.
But didn't the analysis mention string theory having a place for them?
Yes, string theory naturally includes particles of all spins, including 5/2 and higher. They arise as different vibrations of the fundamental string. Think of it like notes on a violin string.
These Reg trajectories.
Exactly. But the catch is, in string theory, these higher spin states are usually predicted to be incredibly massive, like Planck scale massive, way, way beyond anything we can reach experimentally. So spin 5/2 would just be one step on an infinite ladder of mostly inaccessible particles.
So it allows them, but puts them out of reach, mostly. What about that other idea? Holographic duality. Add SCFD.
Right, add SCFT. It's this amazing theoretical tool, a duality between gravity in a specific curved space, anti-de Sitter space, and a quantum field theory on its boundary.
A hologram, sort of.
Kinda, yeah. And interestingly, some of those boundary theories do contain fields with high spins, potentially including spin 5-halves, and they seem to interact consistently within that specific mathematical setup.
So it's like a theoretical lab.
Exactly. It's not necessarily a direct model of our universe at those scales, but it gives us a playground to study how consistent interactions of high-spin fields could work, potentially giving us clues.
Fascinating. Okay, so let's try and bring this together. We went from spin 1/2.
The everyday building blocks, two states, Pauli principle, Dirac equation, well understood. Fermions.
To spin 3/2.
Also fermions, four states.
Mhm.
Mostly composite resonances like deltas or hypothetical stuff like the gravitino. Harder theoretically, Rarita-Schwinger issues.
And finally, spin 5/2.
Fermions again, six states. Not fundamental in the standard model. Purely hypothetical excited states or features of very speculative theories. Even more severe theoretical problems with interactions and renormalizability. No experimental evidence.
There's definitely a pattern here. More spin.
More complexity, more spin states, way harder to build consistent theories for, and apparently much rarer as fundamental particles in nature as we currently see it.
And people are still looking at places like the LHC.
Oh, absolutely. The search for new particles is always ongoing. They look for resonances, those bumps in the data that could signal a new heavy particle decaying.
It'd be a high spin one.
Maybe. Or they look for tiny deviations from what the standard model predicts. Any discrepancy could be a hint of new physics, potentially involving particles with higher spin.
So, wrapping up this deep dive, it feels like we started grounded and ended up way out on the theoretical frontier.
That's a good way to put it. Spin 1/2 is the bedrock. Spin 3/2 is like the interesting, sometimes tricky, next level up, partly mapped, partly speculative. Spin 5/2, that's really pushing the boundaries of what we even know how to think about theoretically.
The main takeaway being that these spin 5/2 particles, fundamentally speaking, are still ghosts in the machine. Theoretical possibilities.
Pretty much. They live in advanced theories, but haven't shown up in reality yet.
And if one did show up,
Game over for the simple standard model. It would be revolutionary. It would demand new physics, new theoretical tools, a whole new chapter.
mind-bending indeed. Okay, so let's leave everyone with this thought to chew on. If spin 5/2 is already so challenging and weird, what if particles with even higher half-integer spins exist? Spin 7/2, 9/2. What kind of universe would that imply? What new rules, new forces, new structures might be out there? How much would we have to rethink?
Yeah, something to ponder.
Thanks for taking this deep dive with us.